now. I'll start recording. So I'll go ahead and give you guys a link here later. So from here on, it will record. So anyway, sequences, first we're going to talk about those. So sequences is basically, it's a special type of function in which the domain is a set of consecutive integers. So in this case here, I have just a small, short little sequence, only has 4 terms. So we have G1, G2, G3, G4. So this is, it's, as I said, it's a special type of function. So the domain is a set of consecutive integers. So for this example here, our domain is, that's what goes into the function. And then of course we get a range value that comes out of the function. So our domain here would be the numbers 1, 2, 3, and 4. Those are what's going in to the function. And then what's coming out are these values here. So instead of using G and then putting a 1 in parentheses like we would do with a normal function, with sequences, we usually use this notation where we have these subscripts. And the subscripts represent those domain values. Okay, so in this case here, our domain values are 1 through 4, and then here are the different terms. So we would say that there's 4 terms in this sequence. And we'd say that the index of each term is that little subscript. So for the first term, our index is 1, then we have 2, 3, and 4. So those are the indices that we have for that sequence. Now, the entire sequence, sometimes if we want to talk about an entire sequence, we'll put the the name, whatever we're calling, in this case it's G, and we'll say G sub K, where K is kind of the general term. In this case it would be ranging from 1 up through 4. But if we put it in these curly braces, then that means we're talking about the entire sequence. Whereas if we would just talk about G sub K, if we say G sub K, then we're talking about just the general term, but maybe we're going to talk about G sub 2, and G sub 2 would be this one right here. But notice when we're talking about individual terms, we don't put the curly braces around them, okay? But if you see the curly braces around this G sub K, you know we're talking about the sequence in general, okay? Now, normally in a sequence, we would start with either a 1 for the index or a 0 for the index. Notice that it's not like sometimes we get used to in computer science, where every time we have something with an index, like a list or something, we assume that it's starting at an index of 0. For our sequence, we can define it to start with any index we want. So most of the time it would start with a 1 or a 0, but it could start with anything that we wanted. We could say, I want to start with an index of 3, and we could for sure do that. So it doesn't matter about that. Now, since it is called a sequence, what's different than a set is that for a sequence, I think all of us know what that word sequence means, and so we would expect this to be true. For a sequence, the order matters. So we really care about the order. It's not like a set where we have elements and we say, well, these elements could appear more than once and there's no special order to them. It's just that these elements are within this set. With a sequence, it's different. We would mean here's the first term, and then here's another term, here's the other, but it's in this specific order. Now we could have a finite sequence where it would start with an initial term and then go to a final term here. And here in the book, I kind of tended to just pull out when they made a definition in the book, I kind of pulled it out from the book. So I called the sequence whatever they called it in the book at the time. So when they were defining a finite sequence, they were calling the sequence A. Okay, so they were calling the sequence A. So A sub M was what they used for the initial term, and then A sub N being what was used for the final term. Now, this could be anything, right? M could start at 1 and we could go all the way up to 4 or whatever. This is just kind of in general. But each time we increase the index by 1 until we get to the final term. So this would represent a finite sequence. And these terms are the actual, entire value that you're going to have for each of these in the sequence. And then the index would be, what we have for the subscript. So here we start with an initial index of M, and we would have a final index of N. But we might also have infinite sequences that go on and on forever. So in this case here, we start out with A sub M. That would be our initial, the M would be the initial index, and A sub M would be our initial term, but we wouldn't have a final term. It would just go on and on forever. Now, it's possible to define a sequence by an explicit formula. So for instance, here you see this green formula. We say A sub k equals 2k for k greater than or equal to 1. So that means that k can be anything from 1 all the way up. It's going to be these integers. So we're not going to have anything like k won't be 1.5, because originally when we talked about sequences, we said that domain is integers, right? So it's going to, if k starts at 1, then the next one would be 2, 3, 4, and so on. So this is an example here. If this is all we were given, A sub k equals 2k for k greater than or equal to 1, we could come up with these first few terms, right? Because we'd say, okay, first of all, what about when k is equal to 1? That's the smallest that k can be. Well, A sub 1 would equal 2 times 1. So that would be a 2. And then when k is equal to 2, we have 2 times 2. So it would be a 4. When k is 3, 2 times 3. Oh, wait. 2 times 3 would be a 6. So this isn't right. 2 times, okay, so this would be a 6 here, right? So if A is at 1, sorry, if k is 1, then we have a 2. Then 2 times 2 is 4. 2 times 3 is 6. 2 times 4 is 16. So that was, I kind of had that in there wrong there. So this is what those first few terms would be for this particular sequence here. Okay. Any questions on that so far? Okay, if not, we'll go on. We have some other little definitions. These are fairly easy. What is an increasing sequence? Well, it's what you would guess it to be. A sequence would be considered increasing if every term is larger than the term before it. Okay, so notice here, 1, 4, 5, 7, 8, it keeps getting bigger. We keep getting bigger terms as we go along. So we would say that this is an increasing sequence. Now, non-decreasing means that it's almost the same as increasing, except that we're allowing for copies of terms. Like here, 5 showed up twice. So we have 1, 4, 5, 5, 8. So each term is at least as big or bigger than the previous term. So just because this term here, the second 5, isn't bigger than 5, that means we can't say it's an increasing sequence, but we could at least say it's non-decreasing, because we're never decreasing as we go on to a new term. We're never going below what the previous term was. Okay, so we have the same kind of thing for the other way. We'd say a sequence is decreasing if, as we keep going with the terms, we're getting lower and lower. And we'd say it's non-increasing if we're either getting lower or we're staying the same. So here we're allowing for this second term to be the very same as the first term. So it can either be the same as the previous term, or less than the previous term in order for us to say it's non-increasing. Okay. Oh, whoops. Oh, man, I'm sorry. I'm finding all these typos. I am so sorry. That's supposed to say decreasing sequence there. Okay. So it's a decreasing. I had that. I had copied and pasted. So it said increasing there. So anyway, but you get the idea, right? Decreasing, it's going down. Non-increasing means it's either going down or staying the same. Okay. Any questions on that? Okay. If not, let's talk about a special kind of sequence called a geometric sequence. So a geometric sequence is a special sequence so that we start with an initial term, which could be anything, and then each subsequent term is found by multiplying the term before by some fixed number that we would call the common ratio. So for instance, for this example, this first example here, we start with an initial term of 5, and then notice I'm going to get the next term by multiplying by 2. So I start with 5. 5 times 2 is 10. 10 times 2 is 20. 20 times 2 is 40, and so on. So I'm multiplying by 2 for that. For this second example here, my initial term is a 2, and then I'm going to be multiplying by 3 as I get more and more. So for the second one, the common ratio would be 3. So 2 times 3 is a 6. 6 times 3 is 18. 8 times 3 is 54, and so on. So those are just two examples. The first one is an infinite geometric sequence because I have the 3 dots saying it's going to go on and on. Whereas the first one is just this finite sequence. It's only got 4 terms. I don't have dots after that. Now, we have a formula that we can use to represent a geometric sequence, okay? And it would look like this. We have S sub k is equal to A times R to the kth. We're going to see some examples and see how this is true. But let's first of all look at this first one here. Look at this first example here. The A is always going to represent that initial term. So for my first sequence up there, my initial term was 5, and then R represents that common ratio. So for that first sequence, I had 2 as the common ratio. So 2 to the k. So if I specified my sequence as S sub k equals 5 times 2 to the k for k greater than or equal to 0. Let's see if we get this thing over here to the right. When k is equal to 0, we have 5 times 2 to the 0th. 2 to the 0th power is just 1, right? 5 times 2 to the 0th power is 5 times 1, which is equal to 5. So we get that first term here. And then the next time, k is 1. So 5 times 2 to the first is equal to 5 times 2, and that's 10. And we get the second term. So we have the first term, second term, and we could keep going, and we keep getting all of the different terms there by making k go bigger and bigger. Okay. And for the second example here, we could see that that would work too, where in this case here, for that second sequence, our initial term is a 2, and our common ratio is 3. So we would define that second one this way. S sub k equals 2 times 3 to the k for k greater than or equal to 0 here. And we could check that out. Oh, but looks like here, actually, if we stop, if we want to make sure we really just get that exact one, we could say k is between 0 and 3, right? Because it starts at 0, 1, 2, 3. And since this wasn't an infinite sequence because I didn't have the dots, then that's what we would want to put for k to specifically get that one. Okay, looks like I wrote over something here. So let's see. I said, we'll just try to look past my writing here. This is an example of something that you will get on like some of the participation activities and maybe a challenge activity too. They say we're given a geometric sequence called S sub n. Now they're calling it S, and they go back and forth. They'll call it A, then they'll call it S, then they'll call a sequence G. Sometimes they call the sequences F. So they're calling it something different all the time. So at this point in the participation activities, they were calling the sequence S. So they said, we've got a geometric sequence, S sub n, and they're saying that the initial term is 3 and the common ratio is 2. So what is, and it says, what is S sub 2? So let's just kind of write out S naught, S sub 1, S sub 2. So if the initial term is 3, then that's this right here. And then to get each other term, we're going to continue to multiply by that common ratio of 2. So 2 times 3 is 6. 3 times 2, starting with 3, multiplying by 2 is 6. Now 6 times 2 is 12. And so S sub 2 would be 12. So that would be the answer here. Here's another question. We've got a geometric sequence. The initial term is 16 and the common ratio is 1/2. Write out the first 5 terms. So we're going to have S naught and then S sub 1, S sub 2, S sub 3, S sub 4, and that will give us the first 5 terms. Okay, so initial term is 16. And then each time to get the next term, we just multiply by the common ratio, which is 1/2 this time. So 1/2 times 16, that's the same thing as like dividing by a 2. So we're going to get an 8. And then we take the 8 times 1/2, and I would get a 4. 4 times 1/2, I get a 2. 2 times 1/2, I would get a 1. Now that's all they ask us to write. But if we kept going, what if they asked us to say the 6th term? Well, then we would take the 1, multiply by 1/2, we get 1/2, right? And it can keep going down. S sub 6 would be 1/4 and so on. So, but to answer their question, the first 5 terms would be these terms right here. Okay, everybody with me? Any questions? Okay, now they also might give you a sequence and they might assure you that it is a geometric sequence. And then they might ask, what is the common ratio? So if you're assured that it's a geometric sequence, then you can take any 2 consecutive terms and divide the divide the largest by the smallest. So let's say I'm going to get rid of this big circle here that I didn't really need. Okay, let's just take any 2 terms. They told us it's a geometric sequence. So we can take any 2 consecutive terms and take the largest divided by the smallest. So 8 divided by 4, and we get 2. And that would be the common ratio. And if this is truly a geometric sequence, we could take any consecutive. So I could have gone 32 divided by 16 and also gotten my common ratio of 2. So that's how you can find that common ratio if you're not given it immediately. You can just take any 2 consecutive terms like that. Okay, now there's another kind of sequence called an arithmetic sequence. So the difference here is we're still starting with an initial term, but instead of continuing to multiply by something, we're going to be adding a number. Okay, so for instance, for this first one here, we start with a 5, and then we're going to add 2. So add 2 to 5 and get a 7. Add 2 again, we get a 9. Add 2, we keep adding 2, and we would get this sequence here. For this one here, the second one, we start with a 2 as the initial term, And it looks like we're adding a 3 each time to get each subsequent term. So these are 2 examples of arithmetic sequences. And just like for the geometric sequence, we can come up with an explicit formula for an arithmetic sequence, and it would look like this. Now they've decided to start calling their sequences T. Okay, so T is going to be the sequence, and the T naught represents our, oh, do I have that here? No, I don't. Okay, I can't remember what I've put in the notes. This T naught represents our initial term. And then the D represents what's being added to each term to get the next one. And that's called the common difference. So that takes place, that's in place of what the common ratio was. It's the common difference. Okay, so we start with the initial term, and then depending upon which n I'm at, I have added that many differences, that many D's. Okay, so here's an example: an infinite arithmetic sequence with initial term 2 and common difference D equals 3 would start at a 2, and then we would just keep adding a 3, and so we could go on and on that way. Okay, here's a question. Let S sub n be an arithmetic sequence. The initial term is 3 and the common difference is -2. What are the first 3 terms? So we'll have S naught and then S1 and S2. Okay, so the initial term is 3, so this would be 3. Now here's a difference here. The common difference is a negative number. And when the common difference was a positive number, we would add that positive number to get the next term. So when it's a negative, you could say that I'm still going to be adding it. But since it's negative, it's almost as if we were, subtracting in a sense, right? I mean, I'm going to be adding a -2, okay? So 3 adding a -2 would give me a 1, right? 3 plus a -2 is a 1. So it's like I'm subtracting a 2, right? So then from 1, we would go then subtract another 2, and I'd get a -1. So that's what I'd get for my first 3 terms if the common difference is -2. Okay, questions on that? Okay, last example for this one here. Let's say we have an arithmetic sequence 7, 4, 1. What's the next term in the sequence? Well, we would realize that starts at 7, and it looks like that we're subtracting 3 from each. So we would know then the next term would be 1 minus 3, which would be a -2. So that -2 would be the next term in that sequence. Okay, so that takes care of our first section, which was on sequences. Okay, so now we're going to talk about recurrence relations. So a recurrence relation is a rule that defines a term, A sub n. A sub n will be kind of like our general term. It defines that term as a function of the previous terms in the sequence. Okay, so you'll see here an example. For an arithmetic sequence, back to that, where we're adding something continually, we could use this recurrence relation to define that. So what this is always going to start with an initial value, and then it's going to have some kind of formula here that defines one term based upon the previous term. Okay, so it says, well, for any general term, take it that if we call it A sub n, then A sub n minus 1 is going to be the previous term, right? That's the previous term. So it says take the previous term and add this common difference, and that gives you your next term. So, so that would be another way besides that formula that we saw earlier to define this thing called an arithmetic sequence. So let's write this sequence 5, 7, 9, 11, 13 as a recurrence relation. So we would say A naught, the first term is the 5. And then we would say A sub n is equal to whatever, and and the order doesn't matter here. I'm not sure why they put the D first. I would have, I think most of the time we would look at and say, well, let's look at the previous term first and see what we need to do with it. But anyway, but they, for some reason, wrote the D first here. So the D here, we see that the common difference is a 2. So we'll go ahead and write it in the order they did. So we'll put the 2, which is the common difference there, and then plus, and then it's the previous term. So I'll say A sub n minus 1. So in order to find, and then I'll say for n greater than or equal to 1. So ask me, what's the 100th term? Well, all I have to do is I have to know the 99th term and then add 2 to it. So as long as you know that previous term, you can find that next term. But it's not very good for finding just let's say the 1,322nd term. We'd have to do some thinking. Well, what would be the term right before that, and so on. So, but as long as we do know all of the terms up till A sub n, but not including that, then it's very easy to find that next one. We just add 2 to it. Okay, so that would be taking an arithmetic series and writing it as a recurrence relation. Here's a geometric sequence that we'll write as a recurrence relation. So they're saying start with the initial value, that initial term, and then you're going to get any term A sub n, we take the previous term and multiply it by r, which is that common ratio that we have for a geometric sequence. So let's see if we can take this geometric sequence and write it as a recurrence relation. So A naught is going to be our very first initial term, which is 5. And then A sub n, any term can be found by taking whatever that common ratio was. And remember, looking back, we had seen when we talked about this earlier, that the second term was the first term times 2. We're always multiplying by 2. Okay, so the common ratio for this is a 2. So we would put a 2 there, because that's our r, times A sub n minus 1, which again is just the previous term. So give me, to find the next term here, I would take the previous term and use that as A sub n minus 1 and multiply by 2. And so I would know then that the next term would be 320. And of course, we want to, kind of say which ends this is for. So we're saying for n greater than or equal to 1, because this isn't true for n equals 0, right? Remember, for n equals 0, we just started with some initial term. So it's only true, this second part's only true when we get to 1 and further on. Okay? Okay, now there's this sequence that the book talks about, and I'd say, go ahead and read the book. You'll be needing to read it in order to get to the parts where you need to do the participation activities and the challenge activities. And they kind of go into this Fibonacci sequence in more detail than I'm going to. This is a common, it's a famous sequence, first studied by this famous mathematician with the last name of Fibonacci. And it talks in the book about kind of how he started out thinking about this. It was really thinking about how the growth of population of rabbits would be, how how that population would grow from month to month, assuming these rabbits are reproduce pretty quickly. So that's kind of where it comes from, where he first started looking at the sequence. But it turns out that this Fibonacci sequence has other applications in other areas too. So this is what it is. Let's see, do I have notes? Oh yeah, okay, all I had was this. So if this is how we describe the Fibonacci sequence using this recurrence relation, let's see if we could come up with, and then I'll have it show up here on the typed version here, but let's see if we could come up with what the sequence would be. Now notice this one's a little different because it has two initial terms, okay? It starts with F naught and F1. So it says F naught is 0 and F1 is 1. Now, anything past that for n greater than or equal to 2, then we define the next term to be the sum of the two previous terms. See, if we're trying to find F sub n, then F sub n minus 1 and F sub n minus 2, those are the two previous terms. So this would be the sum of the two previous terms. Okay, so to find F2, I look at the previous terms and add them together. 0 plus 1 is a 1. To find F sub 3, I look at the two previous terms, add them together. 1 plus 1 is 2. And then F sub 4, 1 plus 2 is 3. And so eventually it kind of starts out slow, but as it grows, it starts to grow, faster. So now F sub 5 would be 2 plus 3, which would be 5. Anyway, that's those were the first few. And if we kept going, we would get these others too. So it starts out 0, 1, 1, 2, 3, 5, as we've just seen, but then it would get to 8, 13, 21, and then, kind of be growing faster and faster like that. So that's called the Fibonacci sequence. I'm not sure that they have you specifically do any of the activities just for this Fibonacci sequence, but that's what the Fibonacci sequence is. And since it's a famous one and we're talking about sequences, we might as well talk about it. So, okay, now, we've talked about arithmetic sequences and how we can put those into, write that as a recurrence relation, and geometric sequence, how we can write that as a recurrence relation, and then of course the Fibonacci sequence. But you can just make up any old recurrence relation. So this is one where it's not none of those others that we've talked about so far. And it was just decided by whoever came up with this sequence. They're calling it F at this point. And as you can tell here, this is going to be part of something similar to what you're going to do for a challenge activity. They'll give you a recurrent relation and then ask for a certain term. So for this one, they made up a sequence that's defined by this recurrence relation. The initial term is F sub 0 equals 2. And then to get any other term, you're going to, if the nth term, or the one that corresponds with the index of n, you're going to square the n and then multiply that by the previous term. So let's see if we can figure that out here. So I'm going to say F naught, F1. They want us to find F3. And on these recurrence relations, you can't just skip to the final one. You kind of have to, since each one depends upon the previous term, we have to kind of find all of them going up to that. So we'll start with the initial term of 2. That's the F naught. Then F1. Well, F1 is going to be 1 squared times F0, right? Because 1 minus 1 is 0. So it's going to be 1 squared times F sub 0. And so that's going to be 1 squared times that previous term of 2. So the answer for F1 would be a 2, right? And then for F2, that's going to be, so the index is a 2, which means we're going to take that 2 and square it. So we're going to have 2 squared times the previous term, which is a 2. And so that's going to be an 8. And so the third term then is going to be that n is now a 3. So we're going to have 3 squared times the previous term. So we're going to have 9 times 8, which is actually equal to 72. So I'm just kind of finding what these are all equal to here. So we would eventually then get 72 for F3. So, you would go in here and put a 72 in that box right there if it asked to find F sub 3. Okay, hopefully that makes sense. Does anybody have any questions on that? We have another example here in a minute. Okay, we'll go ahead and look at this example. This one, you see that they give us 2 initial terms, and then the subsequent terms are going to depend upon the 2 previous terms. The one with the index of n depends upon the 2 terms, the term with the index of n minus 2 and n minus 1. So we'll write that out again here, F0, F1, F2, and they want us to find F4 here. So we've got a 2 here and a 3 here. And for all of the others, it says for any of the others, it says take the 2 previous ones and multiply them together because we have the dot there. So F2 would be 2 times 3, which would be a 6. And then F3 would be the 2 previous terms, 3 times 6, and so that would be 18. And then F3 would be 6 times 18, and that would be, real quick, let's see, 18 times 6, 48, 108, right? Okay, so equals 108. So that would be our answer here, 108, okay? So it's just a matter of understanding how these work, how these recurrence relations work, and then being able to come up with different terms from the recurrence relations. Okay, so that takes care of the second section that we were covering today. So we have just one more section to cover, and that is summations. And so, looking here at this top here, right here, we see it's a sequence, right? Just like what we've talked about before. It's a sequence. We've got different terms, and the index is going from S, and then it's increasing, and then it's going to stop once the index gets up to a T. Well, what if we want to add all of those terms together, all of the terms within the sequence together? Well, this is how we would do it. We would use this summation sign. So this big epsilon here, sigma, that's funny. Yeah, it's a sigma. I don't know why I said epsilon. It looks like an E, I guess, but it's a big sigma. So this is what we use in order for a summation. And what this means here is that so by that sigma there, when we put the I there, we're saying that that's going to be the index. That's my, kind of index is going to vary from one thing to another. But then on the other side of that equal sign is where we're going to start. That's our lower limit. So to read a summation symbol, you actually start at the bottom and you say, okay, I'm going to have this I. This I is going to vary. It's going to start at my lower limit. And in this case, it's a very general limit of S. Normally we would have something there like a 2 or a 1 or something like that. But in this case, it's just going to be an S. And then we have at the top, that says how high it's going to go. So it's going to go all the way up to T. So again, read it from the bottom up. I is going to start at S and it's going to add 1 until it gets all the way up to T. So that would just be the same thing as if we have this sequence over here, right? The first one is A sub S, and then we keep adding 1 to the index until we get up to A sub T. Now we could use any variable for these index, the index of a sum, of a summation symbol, but we usually use I, J's, or K's. Now the book says L's are also common. Now the reason I don't like L's is in some fonts, an L would look like a 1, you know, and that can be confusing. If we're going to use an L, you know, of course, we would want to do like a cursive L or something that looks like that. I haven't seen L used much unless it would be capital L or something, but you know, I wouldn't go so far. You know, usually when you see summations, it's either I, J's, or K's. But again, it doesn't matter what you do, but it's just kind of just like with loops, we as programmers usually would use I's, J's, or K's to represent that counting variable for the loops. Same thing here for these variables for summations. We usually use I's, J's, or K's. So let's look at this. What if I was trying to remember what I had here. If I had to write it out myself or if I had it printed, I guess I have it printed. So what if I gave you this and I asked you to tell me what the value of this is? Well, so you'd say, okay, well, I'm going to be adding up a bunch of terms. J is going to vary. It's going to start as low as 1 and increase by 1 and go up to 4. And so and then all of those different terms, I want to add them all together. So what you would do is just look and see what would be the first term. The first term is when J is equal to 1, and that's 1 to the third, right? J is 1, so we have 1 to the third. Then the next term, J would have gone on to 2, so we have 2 to the third, 3 to the third, and then we go as far up as 4 and stop at 4, and so we have 4 to the third. So this is what that summation means, and then we could find those values, you know, so add up all of those values and we would get 100. So if I told you to evaluate that, you know, summation, you would do this in order to find the value. Now, we would say that there's a couple of different forms represented here. When we have the large sigma sign there, then that is we call that summation form. But then we can also expand it so that we're no longer using that sigma, but we're just showing what it is in reality. And so expanded form would be this other way, the 1 to the third plus 2 to the third and so on. So that would be expanded form. And so sometimes you might be told to expand this summation. And so you would take a summation and then write out the individual terms like this. Okay, one thing to keep in mind is that if what you're summing has more than one term, you need to make sure you put parentheses around it. So for this example here, we're saying that J is going to go from 1 up to N. And sometimes we say stay general like that and say it's just going to go up to N, whatever I want N to be. Or, you know, as we've seen before, we might have a 5 there instead. So, but in this case here, we're just saying 1 and it's going up to N. And we're saying each term is going to be J plus 1. So, you know, we would start with a 1 plus 1, and then we'd have a 2 plus 1 and 3 plus 1 and so on. But some people might tend to just go ahead and write it this way instead without the parentheses. But you could see how this could be confused for something entirely different. We're wanting to have that plus 1 be part of this term that keeps getting added in. But if I wrote it this way without the parentheses, then it could be interpreted as I'm just going to do, you know, this is just the summation here. And I'm just going to add 1 plus 2 plus 3 up to N. And then at the very end, add a little 1 to it, right? So you kind of see how these are two very different things. Do I add a 1 each time I come to a different term? Does this plus 1, is it supposed to be involved each term? I have a plus 1 in there. Or is this little plus 1 just all by itself that I'm just adding once at the very end? Okay, so if you want, if you have more than one term within, um, you know, in this summation here that you want to be involved in each term of the summation, be sure and put parentheses around it so it's known, because it's always going to be, the order of operations given. If it were written like this, second line here, like this, order of operations would say do um, adding or subtracting from left to right, whichever comes first. So I would go 1 plus 2 plus 3 plus 4 up to n, and then just this plus 1 would only happen once. Okay, does that make sense? Anybody have questions on that? Okay, let's do this. I'm going to give you guys a couple of minutes to see if you can come up with answers to these questions. I want you to compute these two different summations and let me know what you think the answers are. So you can type in the chat. When you get the answer to the first question, you might just type it into the chat. And then when you get the answer to the second question, go ahead and type that. We'll still do it together, but I just want to see what some of you get for these before we do it together. I see a couple of people have said 20 for the first answer, and that's correct. So you don't have to type it into the chat from here on for number one if you get 20, but you can go on to the second one and see what you get for that. Okay. Oops. Whoops. Sorry. I'm seeing a 10 for the answer for the second one, and that is correct too. Now I might be hurrying you guys a little bit, but I want to, in case you don't know what to do here, I don't want to just have you sit here and wait to find out what you had to do. So I'll go ahead and start working these. So we would start by saying that J is starting with a 1. So when J is 1, we have 1 squared plus a 2. Okay, and then now J is going to be 2. So we have plus, so this would be like the first little term that comes out of there. And then for when J is equal to 2, we're going to have 2 squared plus a 2. And then plus, and then J goes up to 3. 3 squared plus a 2. Okay, and that's where we stop. J just goes up to 3. So let's see what we have here. It's a 1 plus a 2 plus a 4 plus a 2 plus a 9 plus a 2, and we end up with 20 if we added all of that together. Okay, so that's how we would get that first answer. Now this one here, second one, we're starting with a -1 for J. Okay, so the first one is going to be a -1 squared plus 1. Plus, and now it goes up by 1, so now we have 0 squared plus 1. And then plus, now it goes up to 1. 1 squared plus 1. And then up to 2. 2 squared plus 1. Okay, so we get a -1 squared is a +1, right? So we're going to have a 1 plus a 1 plus, and that's a 0 plus a 1, 0 plus a 1, and a 1 plus a 1 plus a 4 plus a 1. Okay, so 4, 5, 6, 7, 8, 9, 10. We get 10. Okay, so does everybody see how to do that? Any questions on that? Okay, if not, we'll go on. Now we're going to learn a couple of little tricks. Now, these are tricks that at this point you won't really necessarily see why we would need to use these tricks. The book decided to teach you these tricks in this section so that later when you need to perform these tricks, you would be able to do it without having to learn it. Okay, so we're kind of learning it ahead of time so that then when there's a lot more to worry about, we can just refer back to these things that you're learning now. Okay, so again, you're not going to necessarily see why you would need to know how to do this at this point, but we're just going to learn how to do it so that when we do need it, we'll know how to do it. Okay, so the first little trick here is pulling out a final term from a summation. So this first part at the top, it says, if we start with a summation that looks like this. So we're going, K is going from M up to N, and we're summing up a bunch of these terms called A sub K. It's telling us that we can stop one term short. See how we're supposed to go all the way up to N, but we're going to only go up to N minus 1. So we can stop one term short, but those wouldn't be equal because we're short that last term, but we'll specifically write out that last term by itself. And you'll see kind of in this example here what it looks like in reality, because here at this top up here, where I'm working, it's just talking about the terms in general. So you don't really see what's going on. But basically the idea is to stop the summation before the end, before the last term, and then write the last term by itself out to the side. So let's look over here, down here, and this is the kind of thing that you'll have to fill out for your participation exercises. So if we start with this, where we're going to sum up all the I squareds, where I goes from 1 to 7, but we want to pull out the final term. Then instead of going from 1 up to 7, we'll just go 1 up to 6. But then now those aren't equal because there's that final term that's not included on the right-hand side. But what would that final term be? It's going to be when I is 7 and it's 7 squared, right? So the final term would be a 7 squared, which ends up equaling 49. So, if for some reason I would not want to write this as a summation going from 1 to 7, but would rather write it as a summation going from 1 to 6, then I could write it that way and then just tack on this extra 49, and those two expressions are equal. Okay, so I pulled out the final term, wrote it out here, the 49. We'll do another example here. Okay, fill in the missing values such that the final term is pulled out of the summation. Okay, so we're supposed to go from 1 up to 9. We'll just go up from 1 up to 8. And then what should go in here? Well, that last term is going to be when I is equal to 9, and we would have 9 plus 5, which equals 14. So we would put a plus 14 there. And now this right-hand side is equal to the left-hand side, but just written in a different way. Okay, so that's the one trick you're learning, how to pull out a final term. Now here's another trick, changing of variables in summations. So this example here, you see on the left, I have K is going from 1 to N, and I'm wanting to sum up all of the terms K plus 2, and then I cube it. Okay, so I take K plus 2, cube it, and that's a term, and I do that for everything from K going from 1 up to N. Now, again, you might not see at this point why we would ever need to do this, but you'll see later we'll need to do this. And so that's why later you'll realize, that's why we needed to do this. Okay, what if I want to rewrite the summation, but instead of using I want to use K. Oh, no, sorry, it's the other way around. Instead of using K, which is how it started, I want to use I, where this specific relationship is true. I is equal to K plus 3. Okay, so instead of on the summation down below, instead of saying K equals 1, I'm going to say I equals something. Okay, but we're not going to start with 1 because we have this relationship here, I is equal to K plus 3. So when K is equal to 1, what is I? Well, we put, I would equal 1 plus 3, which is equal to a 4, right? So we use that little formula there because we know what the relationship between I and K is, and we can find what K is when I is 1. So when I is 1, K is equal to 4. So instead of starting at 1 like K did, we're going to start, sorry, I forgot I'm supposed to write this in. I didn't have a little text box that's going to pop up. So we're going to put a 4 there. Okay, so we'll have I equals 4 instead of K equals 1. So we would first start by doing that by handling this lower limit. Now let's look at the upper limit. This upper limit is N, but what should it be here if we have this relationship here? Well, so when K is equal to N, what is I? Because it's what I is now. We want I to go from 4 up to what? Okay, so we would say I is equal to when K is N, then I have N plus 3. And so that's what I is when K is equal to N. It's N plus 3. So we would put N plus 3 here. I have to go not just up to N now, but I have to go N plus 3 if I'm working with I. So I start with 4 and go to N plus 3 instead of starting at 1 and going up to N. Okay, so now if we're going to come up with an equivalent equation, an equivalent expression on the right, we have to change what's inside the parentheses here to reflect the fact that we're not going to use K anymore, but we're using I. Okay, so I'm going to erase some of this stuff I have here, up here. And in order to rewrite what's inside here, what's inside the parentheses, I'm actually going to need to rewrite this equation and solve for K. So I'm going to subtract 3 from both sides, and I get I minus 3 equals K. So basically K is equal to I minus 3. So everywhere I saw a K, I'm going to put I minus 3. So I'll say I minus 3, that's the K, and then I have the plus 2. Okay, so I just replaced the K with the I minus 3. Now let's simplify that a little bit. I goes from 4 up to N plus 3, and inside here, I minus 3 plus 2, that's like an I minus 1 to the third. Just combine the negative 3 and the 2. So now here I've rewritten this summation, and now it's all in terms of I instead of in terms of K. And now, and it's a specific I and K that has this specific relationship here, right? Because there would be nothing stopping me from taking this original thing here and just calling K I. I could say, I want I going from 1 to N, and I'll have I plus 2. Well, I've changed the K to I, but that's not what we're doing here. We're specifically changing it to a different variable where there's a relationship already set up, a defined relationship. And so that's what we do for that, is we do this. Okay, any questions on that? I think, do I have another? Yeah, I have another example. So let's do this real quick. And then I have a couple more things to talk about, and then we're done. So here's one more example. We're going to start with this summation I equals 3 up to 21. And we have 1 over I plus 3. And I want to write it in terms of J, but with where we have this relationship here, J equals I plus 2. So I'll start with, down here, I'm going to say J, and then I'll look here and say, when I is 3, what's J? So when I is 3, J is equal to 3 plus 2, which is a 5. So I'm going to start with a 5. And then when I equals 21, J is equal to 21 plus 2, which is 23. So I'll have a 23 here. And then I'll have 1 over, and what do I have here? So when you get to this part, that's when you need to rewrite this in terms of solving for the one variable that's not solved for at this point. So here we have this little equation solved for J. Let's solve it for I. So we would subtract 2 from both sides. So we get J minus 2 equals I. See that? Just subtracted 2 from both sides here. So I have now I is by itself. I've solved for I. I is equal to J minus 2. So then I go back to what was here, and wherever I see an I replace it with J minus 2. So I'm going to have a J minus 2 in place of that I, but then I also have to say plus 3. So I say plus 3. And so I'll simplify that. We still have J going from 5 up to 23. 1 over, and so J, now let's put the negative 2 and the 3 together. Negative 2 plus a positive 3 is a positive 1. So I have J plus 1. So that would be now my new summation if I'm talking about J's with this specific relationship here. Okay, so that was the second trick. So first trick is pulling out the final term. And the second trick is to do this, to rewrite in terms of another variable where we have a certain relationship already between those two variables. Okay, last thing that we talk about today, and that is some of these summations might already have been had a formula it's been proven to be equal to the whole value of the whole summation. So for instance, this arithmetic sequence, we saw before that an arithmetic sequence, well, I don't know if they had in terms of an arithmetic sequence what it would look. Sorry, we talked about sequences, but I'm not sure we talked about a sum of arithmetic sequences. But this would be what it would look like if we're adding up a bunch of terms in an arithmetic sequence, where, remember, this is the initial term. A is the initial term, and then D is the common difference. What this is a theorem that's saying if I have this, then I can actually find that. What if I had like 100 terms? If this was going from K equals 0 up to 99, that would be a lot of terms in order to, to figure out, in order to come up with that. but it's been proven that that entire summation is equal to this thing, which is a closed form. It's just a little formula. And I don't have to find 99 terms or 100 terms. I could just plug things in here. So if I know what A is the initial term, and I know what D is the difference, then I can just plug these different values in to find what the value would be. So this is just in general. So this is just the formula, but let me show you an example here. So this is saying, okay, I've got a summation going from j equals 0 up to j equal 29. Notice here they're writing the j equals 0 and 29 to the side instead of below and above. Sometimes it's written that way, so it means the same thing. But we're starting with 0, going up to 29, and we have this. And they're saying use this formula. So remember that this formula is where A is the initial term. And so the initial term is that what we're starting out with, which would be the 5. So that's the initial term. So that would be A. And then, you know, that difference that we keep adding is the D, right? So 2 is D. They actually have K times D. Here it's D times they just put it in two different, it's in a different order here. K times D as opposed to D times J. Anyway, but the key is picking out A and picking out D. And so now I'll just put it into this formula and I won't have to actually write out all of those terms. So A is 5. So I'll put 5 here times N. Now, notice this is in terms of where we go from 0 up to N minus 1. So what would N be? If this is my summation, what would I say N is here? Anybody want to tell me? Yeah, it would be 30, okay? So does everybody see that? This is N minus 1. So to get N, you just add 1 to that upper limit. So this is 29, so we add 1 to it to get 30, okay? So A times N plus D. D is 2. 2 times N minus 1. N minus 1 is this 29 here, times N, which is 30, divided by 2, like that. The 2's would cancel, so that could help us a bit. So we're going to have 150 plus 29 times 30 is 870. So we end up with 1020. Okay, so 1020 is the answer here. And we found that by using this closed form as opposed to having to add up those 30 different terms. Okay, so that's what a closed form is. So that's the closed form for the sum of terms from an arithmetic sequence. And the last thing we have to talk about is the closed form for the sum of terms in a geometric sequence. So here's for when it's a geometric sequence. For geometric sequence, remember A is still the initial term and R is the common ratio. So we would plug into this formula. So here I've got, they're using L here. L goes from 0 up to 4, and I have 2 times 3 to the L. So the 2 would be the A, and the 3 is what we keep multiplying by, so that would be the R. Okay, so now this says in this formula, we're going 0 up to N minus 1. So since we're going 0 up to 4, then to find N, we would have to just add 1 to that upper limit, right? This is supposed to be N minus 1. So to get N, I have to add 1 to it. So that would be a 5. So let's just plug it into this formula, plug these numbers into this formula here. So I would have a 2 times a 3 to the 5th minus 1 over 3 minus 1. And so that would be a 2 times a 243 minus 1 over 2. 3 minus 1 is a 2. These 2's cancel, and I get 242. So that would be my answer for that one. Okay, so that's what the last part of this section is all about, is learning how to use those closed forms for the arithmetic sequence, sums of terms in an arithmetic sequence, and then sum of terms in a geometric sequence. And so that, I believe, is it. So what I'm going to do is post the notes, so you'll be able to pull up the notes here. I'll also post the recording, so if you want to take a look at that again, you can. And I'll let you guys go, but if you want to ask me questions, stick around and you can ask me questions. Otherwise, I'll see you guys on Wednesday for us to go on and talk about some more things, specifically induction. We've talked about recursion. Now we'll talk about reduction. Induction on Wednesday. Okay, so I'll see you on Wednesday.